Hello, this is Paweł Biernacki. I would like to show you a new AI algorithm called Perkun. So Perkun is in fact a programming language. It is a specific programming language for one specific need. It replaces the if-then construct, known from multiple languages. But if-then is stateless. It doesn't have a state. It doesn't have any memory. It doesn't remember its former actions, nor the history. It ignores the history. And Perkun Optimizer does have a state, a certain attribute called belief. This belief is repeatedly updated after each new input and action performed. Perkun maximizes the expected value of a so-called payoff function. This is also different, so it has some reason to act this way. And it builds a game tree. Hidden variables. This is an important part of Perkun. They are introduced to generate belief. You may say that there is a visible state. It is a vector of input variable values. And for each visible state, we have a number of states that are vectors of hidden variable values. And belief is a probability distribution over such a visible state, over a collection of all states. I will show you an example of a belief and how this distribution works. Now we have two slides, what Perkun needs to know and what it can do for you. What it needs to know are the values, variables, payoff function, model, and game tree height. The variables are input variables, output variables, and hidden variables. The hidden variables being a little special. Now the payoff function is a function in the mathematical sense of the term. It is, I will show you an example of payoff. It is something that tells you how good the input is. Only the input, so no hidden variables are mentioned there. And the model says how the world works. The game tree height tells you how many, or depth, tells you how many steps you are considering. Now what Perkun can do for you? It can predict result probability, it can calculate result interpretation, new belief, but these two capabilities are hidden. They are just secondary. The most important thing that Perkun does is to find optimal decisions. And it is regarding this as performing actions, performing experiments, asking questions. There are no difference in Perkun between actions and experiments. Every action is an experiment and every experiment is an action. Now I would like to introduce PerkunWars. It is a game of mine. I must admit not a very good one, but it is important to understand it, to know how Perkun works. There are three places in the game, Vizima, Novigrad and Shadizar. And there are some NPCs, and there's a vampire. And you, the protagonist in the game, can be in one of the three places, and your objective is to kill the vampire. You can attack the vampire and the best idea is to attack him when the NPCs are around, because they are going to help you. But not all NPCs are the same. The NPCs so there's one NPC called Dorban, who is constantly hunting vampire, and there are two other NPCs who are avoiding him. So the best strategy in the game is to catch the vampire when the NPCs are next to you. Then they are going to help you to hunt him. Running Perkun session. You can watch another video about Perkun that tells you about these two examples. About example 3 Pregor Perkun and example 2 Dorban Perkun. You can enter these values during the sessions to see how the Perkun reacts. What is the belief, and what is the optimal action chosen. Now the optimization algorithm, it is viewed from the top level as 4 steps: get input, interpret it, or build a new belief given the former action and current input, get optimal action, and then you're constructing the gain tree, and execute the optimal action. And whenever you use Perkun in your own project, you can redefine get input and execute. These are virtual functions in C++ in Perkun actual implementation. Now the gain tree. The gain tree is similar to what we have in Minimax, but it differs so that the environment is stochastic. For example, when you consider going to Visima, you may have 2 outcomes of it. Either you will have place Visima true or place Visima false. So you will be in Visima and you will see vampire or not. And depending on which one you take, there's a possibility to predict the probability of each of the outcomes of the results. And for each of them, we are considering a different belief. Yes, so this is a game tree. There are 3 command line tools in Perkun. It is Perkun, Włodkowic, and Żubr. I'm sorry for the names, they all come from Polish. I will not speak much about Włodkowic or Żubr. Włodkowic is just something like Perkun but improved, and Żubr is a Java code generator based on the Perkun algorithm. Now, this is an example of Perkun specification. It omits the values, but you always have the values in the beginning. Then you have variables, and you can see there are 2 input variables. After each variable you have a number of possible values. So there's an input variable, where is Dorban, and do I see vampire, with the possible values false, true. There's also an output variable, action. There are 4 possible actions: do nothing, go to Visima, go to Shadizar, go to Novigrad. And there's one hidden variable, and it is kind of art to introduce hidden variables because you don't perceive them. Apart from that, you have the payoff, which is omitted here, and a model. And the main difficulty in Perkun is to create a model, because the models are usually huge. Then you have command loop 1, which says you're entering the loop, and the depth of the game tree is 1. So you're considering 1 step in the future. Now this is the slide I promised. It is a belief. Belief is a probability distribution over a collection of states. Now we have 3 states here. Where is vampire plays Visima, where is vampire plays Shadizar, and where is vampire plays Novigrad. The first one is impossible. It has probability 0, while the second one, vampire being in Shadizar, has probability 50%, and the probability of vampire to be in Novigrad is 50% as well. You can see that the first variable listed here is a hidden variable, while the 2 other are input variables, and they don't change. So place Visima false, place Visima false, always. The optimal action can be one of the values of the output variable. We may have multiple output variables. Perkun is constructed so that it should deal with this. But in this simple example, we only have one output variable, and these are the possible values. Now, there's an interesting comparison between the payoff functions of Pregor and Dorban. I will remind you that Pregor is someone who's avoiding vampire, Dorban is someone who's hunting vampire. You can see from the payoff function that Pregor is getting 100 points when he's not seeing vampire, while he gets 0 points when he does see him. So what he doesn't like is to see vampire. He likes not to see him, both in Vizima, in Shadizar, and in Novigrad. While Dorban is completely different. Dorban has 100 points for seeing vampire and 0 points for not seeing him. And that's why Dorban is hunting vampire. So if you want to make a game, or if you want to make a system where you avoid something, you give low values to these observations. If you want something to be pursued, you must give high values. The greater the values is, the greater the chance that Perkun will lead to this state. Now there's a separate slide for model. It may have illegal actions and impossible states. Just declarations that some actions are illegal. For example, when you are in Vizima, you can't perform the action go to Vizima. It is forbidden, illegal, and it must be explicitly said in the specification. And impossible state. I will also give you an example. When we are in Vizima and we do see vampire, but the vampire is not in Vizima. This is impossible. He must be there because we can see him. So it allows you. There's a special instruction for that to declare states as impossible. And then there are transition probabilities. The most common instruction in the model is a set instruction. In short, you can have set A, B, C, D, with D being probability of such a transition from the state A when doing action B to jump to the state C. The probability is D. So this is what the set instruction is for. I used the same instruction that I used in the payoff, but it has slightly different syntax, as you can see. Now there's an interesting achievement in the algorithm. Namely, when you have the game tree depth greater than 1, and you have experiments, actions with some neutral payoff differentiating the beliefs, and you have a way to use this knowledge. So actions allow you to get some gain from difference of the belief. Then the algorithm may decide to ask questions, and this is something I consider incredible and quite amazing in this algorithm. Okay, here are the links that you may take. You may download Perkun from SourceForge, PerkunWars also, and you may take a look at my blog at Paweł Biernacki blogspot feed. Okay, thank you very much for watching, and take a look at my other films.